The horror scenario of Eschede is dramatic evidence that technical systems can fail. The fracture of a wheel rim in June 1998 set in motion a fatal chain reaction and claimed more than 100 lives.
Devastating accidents are one of the reasons that motivate manufacturers and scientists to continuously make transportation systems safer. During the past few years, it has been possible to enormously increase the performance of modern rail vehicles. The ICE-3, for instance, reaches a speed of approximately 370 kilometers. Major drivers of this development are electronics and software, but progress in safety must keep pace with the progress in performance at all times.
Nowadays, safety checks before and during approval procedures account for nearly 1/3 of the billions spent on the project budget of a newest generation transportation system. Wherever possible, safety-critical hardware parts are designed redundantly, a process that is the rule for investment goods produced in small quantities. Very high reliability can here be bought with a massive financial effort.
For the software systems, which nowadays take over key functions in the overall system of a rail vehicle, redundancy alone is not enough. Software does not wear out. The fact that each software element as such is of the highest quality is not enough. Rather, the safety of the overall system depends on the complex interaction of components functioning in any situation in a way that precludes safety-critical malfunctions.
The customers of Fraunhofer IESE are system manufacturers who not only need to achieve the highest possible factual software safety, but who must also prove it to the approval authorities. Analyzing the safety of software components in modern transportation systems is one of the major areas of work for the researchers in Kaiserslautern. The prerequisite of any safety analysis is an unambiguous and complete technical documentation available in the form of a model. The integration of subsystems into an overall system presents a major challenge.
The standards of the railroad authorities make it possible for different suppliers to develop according to the same kind of process models and quality standards. Using fault-tree analysis, cause-effect correlations are studied systematically. Starting from a hazardous situation, such as the derailment of a train, possible causes are identified systematically, and it is proven mathematically that the probability of this hazard occurring will not exceed a predefined threshold. By the way, the probability we are talking about here is so low that it is 1,000 times more likely that someone is struck by lightning than that an accident will occur. The use of our fault-tree tools enables us to provide our customers with reliable statements about the risks of the software employed and to use these statements in approval procedures.
Time and again, target conflicts must be mastered here. The approval authorities make safety the measure of quality, whereas for the manufacturers and their customers, for the logistic companies, availability is also a valuable quality. Is a defect serious enough to stop the train, or should it keep going for the time being? Following the prioritization provided by customers, the software makes this decision on its own. The manufacturer must prove that it will do this rapidly and correctly.
Elaborate approval procedures reflect the interest of all stakeholders in the highest possible safety. However, both passengers and operators want better trains, low prices and punctuality. In other words, the availability of trains. This confronts companies with the great challenge of mastering the growing requirements on safety and availability despite the rapidly increasing complexity of the systems. We are working on innovative solutions that will increase safety and the availability of systems and will make it possible to provide more efficient proofs to the approval authorities.
The large transportation system manufacturers market their products worldwide, and the approval guidelines sometimes differ significantly from one country to the next. If the go-ahead is given for Germany, this does not imply automatically that one is also on track towards Russia. IESE provides support in the fast, comprehensive adaptation of safety certificates to the regulations of other countries. This assures market opportunities and provides advantages in time to market.
Our work thus helps manufacturers overcome limits, but it also increasingly transcends the borderline between domains and products. Processes that analyze the safety of complex software systems and trains can be transferred to planes, power plants, and many other investment goods.
One vision that IESE researchers are working on intensively are adaptive software systems, mechanisms that are copied from nature. If we hurt our foot, we walk slower and go easy on it. If the ICE of Eschede could have noticed that one wheel was out of balance, and if the software had then made it react, for example by slowing down or pulling up the wheel, a catastrophe would have been prevented.